Okay, do you see my screen?
Yes. Okay, we are online now. I have the information. Okay, hello, Dr. Jay Pasachoff. Many thanks to be there and talk about the importance of solar eclipses. We Jose now. Okay.
Yes, finally.
Yes, Jose, we are online in YouTube. I press
Hello.
for you the emission. Okay.
Sorry, I have been having lots of problems with my internet connection. Hopefully it stays on, but never know. Okay.
Okay, we are already online on YouTube.
Mhm.
Okay.
Okay, so
Is everything connected? And the Dr. Jay Pasachoff is online and
okay,
ready to start. Can you take the
okay.
session with you? Okay.
Okay,
Fine,
so
and I also had connection problems, and my name is pronounced Pasachoff.
Pasachoff. Okay, that's good to know. That's good to know. Actually, I was gonna call you Pasachoff, so sorry for that. So I don't know. Oops, sorry.
Well, I'm ready to start whenever you.
Okay, so we have. Do we have any indication of? Are there people listening to this?
Do you have a class with you?
Sorry?
Do you have some people with you? A class with you?
No, I'm not. I do not.
yourself.
So all I can say is that so we're here with Dr. Jay Pasachoff. He's a professor of astronomy, scientist and author, and he is the author of many books on astronomy textbooks and also, of course, many scientific article papers. Is an expert on solar eclipses, and he has also
Well, I have lost the sound.
Okay.
Okay, I hear you again.
Yes. I think we lost Jose. Okay, just 1 minute.
I'm back, but my connection really is not working properly.
Okay.
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 Are we on?
Yes. Okay.
Okay, so where are we now?
Just waiting to start.
Okay. So,
shall I start now?
Yes, please. Go ahead.
Okay. It's a great pleasure for me to celebrate this monthly anniversary of the very important 1990 1919 eclipse observed by Eddington from Principe. And I have been observing eclipses myself since 1959, about 40 years after that. And the eclipses continue to be very important scientifically. On the screen, you see a series taken at a recent solar eclipse, but the first four are the partial eclipse that were taken through a filter that lets only about 1/1000% of the sunlight through because the sun is so bright. And only when that goes away do you see the corona that you see on the right side, but also you see some stars. And in 1919, the sun was in front of the Hyades, a cluster of stars, so there were many more stars visible close to the sun than usual, than ever since, in fact. And Einstein took advantage, then Eddington took advantage of that to go to Principe to test Einstein's theory. Here we see four different views of a total eclipse, all taken without a filter. The stars are not particularly showing in this one, but you can see the shape of the corona, and depending on how long an exposure you take, the corona is visible to a different distance. So out from the edge of the sun. So to look at the stars for the Eddington experiment, we have to make sure that we can see the stars through the corona. The closer the stars are to the edge of the sun, the more the deflection is. So we want to see as many stars as possible and see them as close to the sun as possible. A wonderful new book has just come out called No Shadow of a Doubt, the 1919 eclipse that confirmed Einstein's theory of relativity. It's by Daniel Kennefick. It was just published last week. And I have read a copy very carefully, and it really goes into a lot of interesting detail about just what Eddington did in Principe and the whole background, and then a lot of the analysis and some controversy since. And I cover the same things without that much detail in a general survey textbook, The Cosmos, Astronomy in the New Millennium, which is also just coming out. In fact, I'm waiting for the first copies to be delivered to me tomorrow, shipped to me overseas from Cambridge University Press. I'm in Washington, D.C. At the moment, but there's coverage. And as you see in the screen, I've used one of my composite pictures of an eclipse as the cover picture of my new textbooks edition. And that is a composite picture taken at the last eclipse of the sun, total eclipse of the sun, the total eclipse in the August 2017 that was visible in the United States. The first person to draw the path of an eclipse going across the Earth was Edmund Halley for the eclipse of 1715, and you see that that picture on the left there, and he asked people to send in their observations. So this was citizen science even then. I will talk about some of these total eclipses that we have had, and start with the November 3rd, 2013 eclipse that went very near Principe to Gabon. It went about 100 kilometers south of Principe. I wished I could go to Principe and take a boat and go out to the center of totality, but I decided it was important to make the observations from solid land so we could use our telescopes and cameras, and we went to Makangu 2 in the La Lope National Park in Gabon for November 3rd, 2017. The other eclipses shown here are what are called annular eclipses, when two of them, when the May 20th, 2012 and May 10th, 2013, when the moon is a little further than average and the ring of sunlight remains an annulus, a ring, and the sky is too bright to see the stars. But on November 14th, 2012, there was an eclipse that went through Australia and into the Pacific Ocean, and we did observe that one from Australia. And here is a composite view again. We've taken a couple of dozen photographs and taken the best parts of the photographs because the corona varies very greatly in brightness. It's 1,000 times brighter right next to the edge of the sun than it is just one solar radius out. And in this picture, you see the reddish chromosphere, as it's called, to the edge of the sun that's brighter than the corona, and a little bit of the chromosphere on the right is broken off and is exploding outward. And then beyond that, you see some whitish region, and there's one on the left too. Those are called coronal mass ejections. So whenever we see an eclipse, we might get a different structure. The sunspot cycle varies. So this picture was taken at solar maximum, and so there are these streamers all around, and there's just a different corona to see each time. And as we know from the Eddington experiment, there's a different star background if you want to do that experiment. For this 2013 eclipse, I am emphasizing by this picture that there are some spacecraft that can take the outer part in ordinary light, and then on the surface of the sun, which is blocked by the moon, you can paste in an image of the sun taken from space in the far ultraviolet beyond what we can see from Earth. But the sun is monitored by some spacecraft in that way. But that leaves that whole black donut for us to fill in with the eclipse images. And that's what a lot of my research does on the days of eclipses. You can see one of the coronal mass ejections at the bottom. It's rotated 90 degrees from the previous picture. And here is, again, a composite where the gray is where we filled in our view of the corona on the day of the eclipse. And there's an inner spacecraft picture and an outer spacecraft picture. But I emphasize that only in the days of eclipse can we do things like test the theory of relativity from the deflection, and we can see the whole sun. As far as testing relativity, of course, that has been really tested very severely over the 100 years. And we now use quasars that we look through the solar corona very, very near the sun, and can see that much more accurately than we can do the actual optical kind of test that Eddington did. And now we have the gravitational waves that scientists first reported in 2016, and even more recently, we have the image of the giant black hole in the galaxy M87, 55 million light years away from us, in which there was a very recent image made by putting together parts of the best images and the interactions among 8 radio telescopes. So relativity is well established. But that first real test that people belonged was at the eclipse on Principe in 1919, and at the same time from Sobral in Brazil. From the space, those outer images just have a fuzzy image, and here pasted on, we see an image from our ground-based observations, which are just higher resolution than the ones from space. So we do what we can on the days of eclipses. We also take spectra. Starting in the eclipse of 1868, it was realized that there were some extra bright spectral lines that could be seen, and they were so bright they might be seen the day after the eclipse. And Janssen from Paris realized that. And at the bottom, you can see one of the bright spectral lines is in the yellow, and they didn't know what element that came from, so they said it came from helium because it came only from the sun. And then the next year, Young and Harkness in the United States saw a green line that you see there, faintly greenish, a circle, and that's from the corona. So they called that coronium. And as you all know, that helium turned out to be one of the fundamental elements, but coronium is not one of the fundamental elements. It took till 1940 when it was figured out that it was actually iron that had lost 13 of its normal 26 electrons. So it's highly ionized, and that means the gas has to be 1,000,000 degrees or more. And since iron 1 is neutral, iron 14 that's shown there is 13 times ionized iron. The sunspot cycle goes up and down, and sometimes there are more sunspots and sometimes almost none. At the moment, we're at a phase where there are almost none at the extreme right, but the shape of the corona and what is going on the sun varies over a cycle of about 11 years. And at the upper right here, we see several of the spacecraft that have been studying the corona. I am the chair of the working group on solar eclipses of the International Astronomical Union, and we have members from the United States and Russia and Japan and India and Slovakia and China. And now the next eclipses are going through Argentina and Chile, so we've added those people. And then other colleagues from France and the US and the UK and Canada have maintained business kinds of things. In other words, the eclipse maps that so many of us use, the information on how to observe the eclipse safely with the filters that are very important and help with other arrangements. In 2015, there was a total eclipse. There's one on Earth somewhere about every year and a half, and this one went up the Atlantic Ocean in the north. It missed Iceland, it missed Greenland, and as you see there, it went over Longyearbyen, the capital of Svalbard, which is controlled by Norway, just clipped also the Faroe Islands. And I went to Longyearbyen, but not that far from the North Pole. And at that time, we were off the solar maximum. So here you see at the lower left, the sun is not quite as round, but there was a beautifully clear corona there. And we had to be out on the ice because we had to get beyond those mountains. But you can see the shadow go by. This is speeded up by a factor of about 10. I'll play it one more time. So the partial phases are just so bright you don't see any detail, but then the shadow of the moon comes through, and we saw the eclipse for half a minute or so. And we did have the spectra. You can see the yellow line at bottom right. The two fainter little yellow ones were from sodium, and they were known earlier, but the brightest one is from helium. And at the top center, you can see the green line, and at the extreme left in the middle one, the green line from 13 times ionized iron, from million-degree gas, and at the bottom left of center, a little reddish line, and that's from 9 times ionized gas. We did measure the temperature and the effect of the eclipse on the Earth's atmosphere, and it went down to minus 21 degrees Celsius in the middle of the eclipse, and then warmed up after that, and then there are waves that go out in the atmosphere to the side. So we're working with a colleague, Marcos Peñalosa Murillo from Venezuela. We've been monitoring the effect of eclipses on the Earth's atmosphere. In 2016, at the right, you can see the path of an eclipse across Indonesia. And then 2017 at the upper left, the path of a total eclipse across the United States. The other two are annular solar eclipses, which I also observed, but I won't be talking about today. In Indonesia, we had a fairly cloudy sky, but we could see all the eclipse phenomena through a hole in the clouds. We overlooked the ocean, and you can see at the top that we did see all the eclipse phenomena, not the corona not as far out as we might have otherwise. And the two pictures on the left and the right, we needed the filters. And then in 2017, we had an eclipse that came across the United States, and I went to Salem, Oregon to get it as soon as possible when it hit the United States, but then it covered the rest of the United States. And a colleague, Alan Slisky, photographed this wonderful prominence at the edge of the sun. That's hydrogen light, the reddish hydrogen light we call H alpha, and you can see a lot of structure. That's all from the sun's magnetic field. And the magnetic field holds the streamers in place, and you can see this composite image with the big streamers off to the lower left and upper right, and then at the poles, what are called polar plumes, which are like the magnetic field lines that come out the edge of a bar magnet. So we're learning about the magnetism of the stars. And let me stress that we see all this in detail for the sun, and that's the only sun for which we can see this detail, but we know that that same detail persists in billions and trillions of other stars. So the sun is a close-up laboratory that tells us about all the stars. We were observing from Willamette University. I had some colleagues with us. We had 8 of my undergraduate students from Williams College and several of our alumni who were astronomers or graduate students there. And we were on a terrace that you can see in the picture there. Here's our Williams College team of some alumni and current students. And we had with us a team from Yunnan in China and a team from the Kyoto Observatory in Japan. So the studies are very international. And here's the composite of the eclipse as it went on. What we're studying is how the corona is very hot. It's millions of degrees, but it's over a level of the sun that's only about 6,000 degrees Celsius. I'm talking Celsius degrees now. And the core is 15 million degrees. So somehow this energy is generated in the core by fusion. And by the time it reaches the surface, it's much cooler. But then the corona is hotter again. And one of the big science questions is, why is the corona millions of degrees when it's above 6,000 degree gas? So energy is being injected into this sparsely populated gas, and it makes the particles of the coronal gas go very fast, and that's what we call millions of degrees. So to do that, we try to go to the various eclipses and study the spectrum of the corona and how it changes with the sunspot cycle, and to look for fast variations in the corona to see what could be causing the heating. Here is a composite image again. You see how our eclipse image fills in that donut that's otherwise uncovered from the spacecraft around, and then pasted over the black silhouette of the moon in the middle, a different spacecraft observation. Here is a weather satellite map. You can see the shadow of the moon go across the Earth, in this case, the United States. So these are real phenomena. To be in an eclipse, if the American spacecraft on the moon, the Lunar Reconnaissance Observatory, could see that shadow also. And if you were at the International Space Station, you could just put your camera to the window and look out and actually see that shadow crossing the Earth. I'd love to be able to do that one day. Here, we took some our observations, and then 65 minutes later, the path of totality had gone to the east, and you can see this feature, for example, has changed so much in only about an hour. So there are huge velocities going on the sun, and we've been measuring those. You can see some changes, some big changes here too. So we're studying those, but we are at the bottom of the sunspot cycle now. And most days in 2018 and 2019, there were no sunspots on the sun at all, and sometimes there's just one sunspot, which gives about that level, and that's very different from dozens and dozens of sunspots at the solar maximum in 2014. And you can see that over hundreds of years, the cycle has gone up and down, and you can see that in 1919, the Eddington on Principe and Sundy got about halfway between the maximum and the minimum. So there were a few dozen sunspots on the sun at the time. That didn't affect his observations. But for studying the temperature of the sun, which I do, that does vary with the solar activity cycle. Here's a faint red line and an even fainter green line. And depending on the phase of the sunspot cycle, we can take the ratio of the intensities of those two and see how the coronal temperature changes. Here's a composite with a new weather satellite image pasted in the middle. Some bright person figured out that the weather satellites are looking down on the Earth, but they have solar panels pointing at the sun. So now we have solar telescopes in the solar panels, and this is a system called the GOES, G-O-E-S, spacecraft. And there are two that have been launched recently, and they're taking a series of 6 images in different temperatures. And just to remind you what solar maximum looks like, this is going back 20 years, but at solar maximum you can see that there are streamers all around, and we don't see those polar plumes because they're hidden by the streamers. Whereas now, most recently, from the GOES 16, you can see the streamers and just a few of those just a few of those streamers and see the polar plumes. We also used radio telescopes that we've just drawn in the moon, but as the moon covers and uncovers the sunspot regions, which show here in the radio, we can tell exactly where they are very precisely, even more precisely than we can with the big sets of radio telescopes. Even the very large array, which you see here in a drawing by a former student of mine, they can synthesize the sun at high resolution, spatial resolution, but we can do even better with the eclipse. And then I was working with a group of people in something we call the mega movie, in which people, just ordinary students and others all across the United States, made images, and they have been put together into a video, and we have a big set of observations that can be studied now to see the progress of the eclipse across the country and changes in the eclipse. And so there's a website for the mega movie, such as eclipsemega.movie, in which you can see more detail about that. And then NASA has some spacecraft that are not looking at the sun from the same angle that the Earth is, but are partway around and could get therefore a three-dimensional view of the sun and on the days of eclipses. And this is called stereo, solar terrestrial, etc. But it came out to stereo because it's 3D, and so we have the images of 3D of where those streamers are. This solar ultraviolet imager that's on the weather satellites just gives wonderful data all the time. And this is not on eclipse day, but shows you the kinds of high resolution data, the eruptions that can be followed whenever they occur, because the spacecraft is watching the sun all the time. A lot of links and observations and when you can see the next eclipse is posted at my website at totalsolareclipse.org, which are my 70 eclipses that I've seen so far and worked on. And then at eclipses.info, that is a site that I run for the International Astronomical Union. So there you can link to all kinds of maps of when the eclipses are and see the paths of the eclipses. And then I worked on a couple of summary articles that are listed here in the American Journal of Physics and Nature Astronomy about articles about eclipses and various tests of things, including the tests of Einsteinian relativity. And I'm very glad to have had major support from the National Science Foundation and the National Geographic Society, and we had some additional support for students from NASA and by the Sigma Xi Honorary Society and from Williams College, where I'm a professor, and the Carnegie Institution is where I am on sabbatical this semester at the Carnegie Observatories in Pasadena, California. I said before that there's a total eclipse of the sun about every 18 months or so, and in the year 2018 it happened that there was no total or annular eclipse. So we went to see the partial eclipses, and there were 4 partial eclipses, 3 in 2018, 1 in early 2019, between the total eclipses. And so first we went in February to Buenos Aires and saw this eclipse really very, very nicely. And then in July, the eclipse was over Antarctica and just clipped the bottom of Australia, and we were able to go to a radio telescope that they run in Australia. The kinds of observations here, they're observing pulsars, and that's the kind of things that you can use to test relativity also. And we had a nice partial eclipse there, and 10% coverage of the diameter of the sun was what we got from that location. And then in Sweden, there was a bigger eclipse, and here's a picture from Stockholm, and also a picture from the spacecraft to show the moon blocking the sun in the ultraviolet. And then in January of 2019, this year, the Pacific Ocean and East Asia had a partial eclipse, and I was at Tokyo, the National Optical Astronomy of Japan, with my colleagues at their flare telescope, solar flare telescope, to see the eclipse. And then sometimes in space, from high up in space, they get an extra eclipse. In February, there was an eclipse that was seen from the spacecraft high above the Earth that we didn't see from the Earth's surface at all. So that's fun to have these extra eclipses. The next total solar eclipse will be on July 2nd, and I'm very busy in the planning of that. And I'll be at the center line north of La Serena, which is north of Santiago in Chile. And the eclipse will have come over a lot of the Pacific and be low in the sky, only 13 degrees above the horizon when it reaches us. And then I also have some possibility to observe from the Cerro Tololo Inter-American Observatory at 2,200 meters of altitude, 7,500 feet. And I'm obligated at this centerline site, but I've arranged for 4 of my team to go to the top of Cerro Tololo with some interesting instrumentation. It includes Aris Vulgaris from Thessaloniki in Greece with some spectrographs and a special filter that he's modified to study argon gas that has, in the corona, that has been argon 10, that's lost 9 of its electrons, so again, million-degree gas. And Kevin Reardon will work with him on imaging and the spectroscopy, and Alan Slisky and David Slisky will do high-resolution imaging. You saw a prominence image from one of them earlier. So that's July 2nd, 2019, and they'll be on the top of the Cerro Tololo Inter-American Observatory. That's not right at the center line, but we'll still have over 2 minutes of totality. And then the Las Campanas Observatory is just outside, run by the Carnegie Institution of Washington, just outside totality. So those people have to drive into totality in order to see the effects. And then the 2019 eclipse goes over the Pacific into South America, and then the 2020 also goes in Pacific and Atlantic and over Chile and Argentina. So we'll be on the Atlantic coast of Argentina for that one. And then at the bottom, you see 2021, the eclipse is only over Antarctica and the ocean and near that. And there'll be some ships that go out for a few weeks and some airplanes that overfly. And then in 2023, there's an eclipse on the other side of the world that just clips a bit of Australia and goes over East Timor. And then back in the United States, at the top there, you see in 2024, goes over Mexico and the United States and Eastern Canada. Here's the path for 2020, where you see the peak is over Argentina, and we'll be in Las Grutas on the coast there, and just very close to the center line, which is a couple of 100 kilometers across. And then in the United States, we have an annular eclipse in 2023 and a total eclipse in 2024. If you're off to the side and seeing only partial phase, it doesn't matter whether it's from an annular eclipse or a total eclipse. It just matters what percentage that you will get. But many people in the United States are looking forward to the annular eclipse of 2023. And so there'll be partial phases through the whole country and a total eclipse in 2024. And there is no European partial eclipse very soon. So here is our site. From Oregon, 2017. In the horizon, we're seeing far enough away that they're out of the zone of totality. So think of yourself being in the middle of the shadow of the moon. You can see the corona at the top with the black moon silhouette, blocking out the view of the sun behind, keeping that sunlight from hitting the Earth's atmosphere. So this was a 2-minute eclipse, and you can see that when you're actually in it, 2 minutes seems pretty long. You can take a lot of photos, and in fact, first-timers, we hope you just look up, not even take photos, or you'll miss these wonderful phenomena.
Wow.
Then you can begin to see the shadow disappear from the right, gets a little brighter. The diamond ring. There I am at the right with a filter. So it was just a wonderful experience. And I can't stress enough how important it is to be in the zone of totality, even if you're 10 miles, 10 kilometers outside the zone of totality. You miss all those wonderful phenomena. Here in Washington, D.C., yesterday I went to a museum, National Museum of American History, and they had a ticket booth from Yankee Stadium, the baseball stadium in New York, and a ticket booth from the stadium that was erected almost 100 years ago. And an example I can give is say I went down to buy my tickets to a game, to a football game or a baseball game or whatever, and then I just bought the tickets and I went home, and somebody said, "Where did you go?" And I said, "Well, I went to the stadium." And that's a correct statement. But nonetheless, even though I went to the stadium, I didn't see the game. I didn't see the event. And the same with an eclipse. If you are just in a partial eclipse, you've missed the main event. It's important to be in the zone of totality. Only there does the sun entirely get blocked out by the moon. Only then do stars and planets appear in the sky. And that's what allowed the Eddington in Principe and the Astronomer Royal, Dyson, helped back in England with analyzing data from with Eddington and with the group from Sobral in Brazil. And so we needed those special circumstances. And it's a wonderful 100th anniversary now. We have all these wonderful new methods, but it's still very interesting to observe the sun at eclipses and to make scientific results from those observations. So I thank you very much for the invitation to participate in this anniversary of the Eddington observations, and good luck to you all.
Well, thank you, Dr. Pasachoff. Sorry. I was wondering if I can put some questions just to.
Of course.
Okay, so we have now spacecraft that are observing the sun all the time, right?
But I showed you those images where the spacecraft have to block out the sun. They can't make as good an eclipse as we make with the moon. So there's that whole region outside the sun that the spacecraft can't observe. Yes, and that was where I was going, because nonetheless, observing eclipses and registering data is still very important, right? That's correct. Yes, and for you, you travel to see eclipses and carry your own instruments, of course, but for many people, it's just the emotional experience of experiencing a solar eclipse. So I was wondering how much or what kind of instruments do you carry other than cameras? Well, in order to really see the corona, you need a lens, telephoto lens of at least 400 millimeters. Okay. So we would have lenses or telescopes between 400 millimeters and 1,000 millimeters to make those images. Okay. One other thing that I was curious about is, is there any kind of cycle that we can predict the pathways of future eclipses? In the sense that they go back to the same place? Well, if you're in one place on the Earth, on the average, it's another 300 plus years before it comes back to you. Okay. But it was discovered thousands of years ago that essentially the period of the sun and the moon that go around brings a similar eclipse back after 18 years, 11 1/3 days. But 1/3 of a day means the Earth has rotated 1/3 of the way.
Okay,
so
sure.
it's only it's only 3 of those, or 54 years and a little over a month, that an eclipse reappears. So there are some historical questions. Could people back thousands of years ago have really figured this out? Now we know that that we do get a similar eclipse back after what's called the Saros of 18 years, 11 1/3 days.
Yes, because, well, we're out of luck here in Portugal. At least we haven't seen a decent total solar eclipse for a long time. Well, it's just bad luck, I guess. One other thing is traveling around the world and watching eclipses from all those places. You must have collected some stories about reaction of local people.
Yes, well, the local people are always very interested, and we take advantage of the interest in the eclipse to teach a lot about astronomy, not just about solar eclipses. So the outreach is a very important part of our work at Eclipses.
Sure, and some people that have witnessed total solar eclipses have told me about the reaction of animals, actually.
Yes, so the animals, they get confused and they think it's night, and the cows will go back to the barn, and the chickens will stop, and the rooster may crow when the sun comes out at the end, and so people have been watching various the birds become quiet. So there are biology interested people who are also studying eclipses.
Yes, so eclipses have still a lot of things to teach us, and well, I believe they're one of the most beautiful natural spectacles in the world, right?
Yes, and for those listening, just put on your list of things you want to do in your life to travel into the totality to see a total eclipse.
Yes, okay. I don't know if there's any more questions. I don't think so. So I thank you again very much for this wonderful presentation, and hope to meet you sometime around the world watching a solar eclipse, hopefully.
Yes, thank you very much. I'm glad to see you at an eclipse or otherwise. Goodbye.
Bye-bye.